Hello, Year 10. Hope you're well. Here's a little bit of feedback on the specific latent heat practical, the one where you watched a video and I melted some ice and I measured the mass of the melted ice and we used the amount of energy to find out the specific latent heat of fusion of water, which, if you remember, is the amount of heat energy required to melt exactly 1 kilogram of ice. Okay, so let me just run you through the calculations. So there's the apparatus that I set up. The only difference is instead of one filter funnel with ice, I had two, because if you remember, I had a control as well, didn't I? The reason for that is because ice melts anyway if it's at room temperature. So we want to measure the amount of ice only measured, only melted by the heater. So what we do, we have a second one just sat there collecting, and that's going to have ice melting due to just the room temperature itself. So that's why we had the second one, so that we could subtract the mass of water collected there from the mass of water collected there. And that should give us the mass of the water melted by the heater itself. So anyway, that's you watched the video, right? What values did I measure? Let's get some written down. The first thing I noticed when looking at your set of calculations was units. There's a real lack of units with a lot of you, so you need to sort that out. Whenever you write down a measurement, you've got to write down its units, and it's really important, especially if you need to convert units, right? Because you need to know what things are measured in. So we had two conical flasks, didn't we? We had conical flask A and B. So A, we're looking, I think that was 97.56 grams, wasn't it? And B was heavier, 117.03 grams. So that was the mass of the two beakers. All right. Now, when they both had melted ice, so A was 125.45 grams, and B was 127.76 grams. Right, subtracting the mass of the beakers from these values gives us mass of the melted ice for A was 27.89 grams, and for B it was 10.73 grams. Now that should make sense because it was A that had the heater in it, so that's obviously going to have more melted ice. All right, but this is why we used B, because this is just the mass of the ice that melts due to room temperature. So if we subtract this value from this value, then we've got our value of ice melted by the heater only. So subtracting those two values gives us 17.16. So that's the amount of ice melted by only the heater. Okay. Now you might notice that is in, because I've written down the units, I can see it's not a standard unit. So what I would do here is get that into standard units. So standard unit of mass is the kilogram. So I'm going to go all right at this point, 0.0. I'm going to divide this by 1,000, haven't I? 0.01716 kilograms. So that's the mass of the ice melted by the heater only. Right, how much energy went into melting this much ice? Okay, how much energy exactly? Well, if you read the notes I gave, it actually maxes out. So I didn't mention this in the video, but the heater, the joule meter, which is measuring the amount of energy in joules, it maxed out at 10,000 joules, and that's when I stopped the heating process. So our energy in is 10,000 joules, making sure I write the unit because it could be kilojoules. Right, we're using the equation now, aren't we? E equals ml. So What was our M again? 0.0176. So, rearranging this equation, it becomes L equals energy over mass. Energy was 10, 1, 2, 3, all over 0.01716. That gives us a value of 582,500. Now, what is the unit? What is the unit of L? That's absolutely crucial at this point because quite a few of you just wrote down this number without any unit at all. So, if L is energy over mass, it's going to be, what's the unit of energy? Joule. What's the energy of the mass? Kilograms. So it's joules per kilogram. Joules per kilogram. Absolutely crucial. Right, now I asked you to use the internet to find the actual value, okay? Because this is a known value. All ice has the same specific latent heat. All pure ice has the same value of specific latent heat, okay? So the value you should have found from the internet, I believe, was 334, 334. Now it's 1,000, 1, 2, 3. So a few of you found 334 kilojoules per kilogram, and you just wrote 334. But we have to have the same units here. So it's 334,000 joules per kilogram. So there you have it. There is our measured value. There is our actual value. Now, there's quite a big difference. Now, I'm not going to start getting upset by this because there's a very real reason why we have this measured value compared to this value. The main important thing is, the really important thing, it's of the same order, okay? It's in the hundreds of thousands, so that's fine. If we were out by a factor of 1,000, then there'd be an issue. There'd be something wrong with our calculations. So that's how it compares. The measured value is considerably higher than the real value. So, what is the reason? Okay, a few of you came up with a few reasons. A couple of you said that in the control, maybe the ice was different sized chunks. Maybe it was more, maybe it was more crushed and would melt more quickly. Maybe it was a different temperature to this ice here. Well, if you noticed in the video, I took the crushed ice from the same container and I tried to make sure that it was the same consistency in each funnel. Okay, right. Like I said, there's a very, very obvious and very real reason. How much energy did we measure on the joule meter? If you remember, it maxed out at 10,000 joules. Now, did all of that 10,000 joules go into melting ice? That's a very, very big question, isn't it? The answer is no. And the real answer is not even close. In fact, a lot of energy, quite a big portion of that 10,000 joules goes into the atmosphere. Okay. Sure, some of that goes into melting the ice, but a lot of it is given out, is wasted into the room. Some of it might go into heating up the filter funnel. Okay, but only some of this 10,000 joules actually goes into melting the ice. So there you have it. That's the real reason. Not a brilliant practical, not a brilliant method, but it's a very, very, very useful one for starting to get us thinking about errors and uncertainties in measurements and practical techniques. So, anything doesn't make sense, please get in touch. Please post on the stream, or you can message me privately. But I will see you in the next video. Thank you very much and have a great weekend. Goodbye.